So it's really a pleasure to be able to talk to you all today, because this is the first time that I'm able to present some of the most important parts of my PhD work. So thank you all for being my guinea pigs. I'm going to be giving you a bit of a chart rundown of the top smash hit surface melt drivers on the Larsen C ice shelf. So brace yourselves for lots of bad puns about top of the pops. So a brief introduction to anyone who isn't familiar with the Larsen C ice shelf. It's the largest remaining ice shelf on the Antarctic Peninsula. And the Antarctic Peninsula is this bit up here that sticks out of the Antarctic continent. It's around about 48,000 square kilometers, or at least it is post the carving of a gigantic iceberg in July 2017. And the main research question that I'm interested in is unpicking what the main drivers of surface melting are on this ice shelf on Larsen C. Now, the reason I'm interested in this is because over the last 60, 70 years, more than half of the ice shelves around the Antarctic Peninsula have lost mass, either via thinning or receding, or in some cases collapsing entirely. So that's what this picture, or the series of images, shows on the right here. It's over the course of 6 weeks or so, the Larsen B ice shelf, which previously in spectacular fashion. So I think the first image is from January the 31st, and the last one is sometime in March 2002. So it collapsed over a short amount of time. And we know that that ice shelf collapse was primarily driven by surface melting, and that surface melt was able to enter existing cracks and rifts in the ice shelf and cause a process called hydrofracturing, whereby those cracks eventually widen and deepen so much that they reach the bottom of the ice shelf and cause pretty catastrophic massive disintegration events like we saw there. So we know that the first order cause of that collapse was surface melting, but the real question is what causes that surface melting in the first place. And it being Antarctica, there are relatively few observations that we can use to unpick that question. The limitations of satellites at high latitudes and the relatively short time series that we have mean that models are a really helpful tool to understand the processes going on. Now, the only thing is that lots of atmospheric models fail to reproduce the observed patterns of surface melting that we see on the ice shelf. So on the left-hand side here, hopefully you can see my pointer, we've got a composited image of mean annual melt duration. So the number of days every year where melting is occurring. And this is from a paper by Suzanne Bevan, and it's taken from satellite observations between 1999 and 2017. And what we can see is that there is a general north-south gradient in the amount of melting that occurs. And this is kind of what we expect from the latitudinal variation of temperature and of solar radiation. But then importantly, superimposed upon that is this east-west gradient. So you can see there are more melt days per year observed in these inlets, which are close to the mountains. Now, the problem is that lots of atmospheric models don't really capture this pattern. So you can see that AMPS, RACMO, and MAR, all of which are quite commonly used to simulate conditions in the Antarctic Peninsula, all get the north-south gradient quite well, but they don't necessarily capture this east to west variation, and that's a problem. So we need to be able to capture the processes that are driving the melting if we're confident that we can use it to understand what's going on and how this might affect ice shelves in the future. So we thankfully have lots of data and observations now around the Larsen C ice shelf, but it's not a very long time series. So we can use these to understand their processes. But of course, the thing about weather stations, so some of the weather stations around are shown here, are that they're only single points and that the time series are relatively short. The great thing about computer models is that they can show you processes in 3 dimensions. So we can measure surface meteorology, but we can also measure a whole suite of other things at the same time to get an idea of the things that are causing surface melting. One of the most important concepts that I'm going to be talking about here is the surface energy balance. So just a brief overview for anyone who's not familiar. The surface energy balance refers to the total amount of energy that's received at the surface. In this case, it's the Larsen C ice shelf. And it's essentially the balance between different flows of energy that are coming towards and away from the ice shelf. So the main component throughout the year is the shortwave, the solar radiation flux. But then we've also got long wave radiation emitted by the Earth, absorbed and re-emitted back down to the surface by the atmosphere and clouds. We've got turbulent fluxes of sensible and latent heat. Then we've got a very small term called the ground heat flux, which is the conduction of heat into the ice shelf. Now, if we add all of these together, we get a number called E tote, or what I call E tote, which is basically the total of all of them. And crucially, if the surface temperature is greater than 0, i.e. if it's at the melting point, then you can see melting occurring. So you need to have a positive E tote and a positive or 0 surface temperature for melting to occur. Brief synopsis of the method. I won't bore you with the details, but we're running the Met Office unified model in what I'm going to call a nested configuration. So it's dynamically downscaling global scale information to a high resolution in a nest, which is 4 kilometers horizontal grid spacing here. So it takes its lateral boundary conditions from the global model. It's using prescribed SSTs and sea ice here, so it's just an atmosphere only model. And if you're interested in the details of the configuration, there's some references here. So overall, this is a kind of general schematic of the method. So I'm forcing this global scale MetUM model with era interim reanalysis data for the period 1998 to 2017. And era interim is shown to be probably the best all-rounder in terms of the reanalyses in the Antarctic Peninsula region. Then I'm using that information to drive that global model. The inner domain takes its lateral boundary conditions, so around the edge, it takes all the stuff that's going on in the global domain and uses that to run the simulation at much higher resolution over this specific region that we're interested in. I do this every single 12 hours. We initialize the model with era interim, and then it runs 24-hour forecasts. So we actually discard the first 12 hours of each forecast and just stitch together the latter half of each of those forecasts to get a 20-year time series. And that produces both 2-dimensional and 3-dimensional fields. Once we've got all the outputs, then we can validate them against the available data. This is things like automatic weather station data on the ice shelf. And if we're confident that it does a reasonable job at representing those, then we can start to think about the analysis. And that's where we start using the outputs like this here. So for the rest of this, I'm just probably going to mention hindcast, and that's what hopefully you will know what I'm talking about. So very briefly, because the validation is always the least exciting part, I just want to convince you that the MetUM is doing a reasonable job of representing conditions. So I've got modeled versus observed variables for temperature, surface air, relative humidity, wind speed, downwelling solar and long wave radiation, net radiation, and then the melt flux. So here, all the dashed lines are a kind of perfect one-to-one line, and the solid line is the actual relationship. This is from the weather station that we have the most complete data set for. And you can see that overall it does a pretty good job. There's generally quite good agreement. There's a slight warm bias, particularly colder temperatures, which I suspect is to do with the representation of stable boundary layers. This leads to some biases in the surface energy balance, particularly with the upwelling long wave term, which means that we get a bias in the amount of net radiation, and that translates into an underestimate in the melt flux. Now, the thing we're interested in is, of course, the melting. So if we go back to look at this figure of our melt duration taken from this Bevan paper from satellites, I'm trying to reproduce this gradient, this east-west gradient. And that's what you're seeing on the right here. This is the annual mean cumulative surface melt amount in melt seasons. So rather than having years, we're going for the whole melt season, assuming that the melt begins in August and ends in July. So this is the way glaciologists, I believe, often do it in Antarctica, because the summertime straddles 2 years. So what we can see is that there is lots of interannual variability. Some years are much higher melting than others, but crucially, and most importantly for me and my hindcast, we can see that it's reproducing this east-west gradient, and that's really good news. So we can be confident that the MetUM is capturing the processes that are driving surface melting sufficiently so that we get this east-west gradient, and that's really great. So I think, as far as I know, this is the first time, or the first model, the MetUM is the first model to be able to do this, which is really great news. So hopefully you're sufficiently convinced that it's worthwhile using the MetUM to look at the drivers of surface melting. So this is just a reminder of our research questions. And to have a look at that research question, I've done two main things, so two primary analysis methods. And the first one is to look at the relationships between model variables to understand how they interact. And I've just looked very briefly at correlation coefficients to give a kind of first glance of the things that are important. And then secondly, I've used this concept of regimes. So these kinds of regimes are things that I've identified from the literature or from general knowledge of the Larsen C ice shelf that I know may be important in causing surface melting. So that's things like the southern annular mode, El Nino, Fern events, this kind of thing. And I'm diagnosing those regimes and producing composites of the mean conditions when those conditions are diagnosed. So this is quite an important concept, so I'm going to go into a little bit more depth on that. For some things, such as SAM and ENSO, those regimes can be diagnosed using observed indices, and that's what I've done. Then we've got other regimes that must be kind of diagnosed from model variables. So for example, if I'm interested in understanding the effect of cloud over Larsen C on surface melting, then it makes sense for me to diagnose those cloudy conditions by looking at the cloud fraction averaged over Larsen C and then using some kind of threshold. So that's what I've done for the cloudy regime, for example, when cloud fraction is above a threshold over Larsen A, all the conditions during those time periods to get this composite. And I've got quite a few regimes, there's a long list, and I do a similar kind of methodology for each of those. And I'm looking at things like cloudy versus clear conditions, cross-peninsula flow, which is indicative of Fern winds, more on those later, barrier winds, high and low melt, all of these things, and they're summarized in this table here. Now, one note of caution is that the regimes are absolutely not independent, and in fact, many of them are related. So we might expect positive SAM conditions to lead to cross-peninsula flow, for example, which may then contribute to Fern events. And some of them happen at the same time. Now, the most exciting bit, the moment you've all been waiting for, the official charts, the top 4 surface melting on Larsen C smash hits. So in at number 1, we've got solar shortwave radiation. So shortwave radiation is the first order driver of surface melting on the ice shelf, which is probably unsurprising to many of you. 90% of melting occurs during the summer, which is December, January, February, for those who are not familiar with the Southern Hemisphere. And this shortwave radiation dominates the surface energy balance. And it makes sense when we think that in the summer you have 24-hour daylight. Annually, if we consider it annually, the highest correlation between melt flux and any other flux is with shortwave net radiation. And cloud plays quite an important role in determining the amount of shortwave radiation that we receive at the surface, which is nice for me because it's consistent with the paper that we published earlier in the year. So that's nice to see the translation across. Now, I mentioned that cloud can influence the amount of solar, but indirectly look at the effect of shortwave on the ice shelf and melting. So here we've got the first of many composite plots that you're going to see. So hopefully you won't get too bored of these by the end. I'll explain them briefly. So here on the left, we've got the mean surface meteorological conditions during. So here we've got color contours, which show you the mean daily maximum 1.5 meter air temperature anomaly, which is quite a mouthful. So I'm going to be saying Tmax anomalies from now on. So added to that, we've got vectors, which indicate the 10 meter wind speed and direction. And here's a nice scale for reference. And then after that, we've got some contours which show you the mean sea level pressure. Melt flux anomalies, and in both cases, the redder colours mean positive and the blue colours mean negative. So during this clear summertime conditions, we see that the additional solar radiation that reaches the surface drives positive Tmax anomalies and also positive melt flux anomalies. And there's some suggestion that this may be related to Fern-induced cloud clearance, and shows you the interrelationship between the regimes. Now, I've said the word Fern quite a lot, but I have failed to give a good definition so far. So now is the time. So Fern winds are these warm, dry winds that are formed when air flows over steep terrain. So that includes the mountains of the Antarctic Peninsula, which can be up to 2,000 meters tall. When we get this airflow across the mountains, that causes temperatures and wind speeds to rise and humidity to fall on the other side. So there's this warming and drying effect, and that comes with associated sensible and latent, well, negative latent heat fluxes. So Fern winds are the second most important driver of surface melting on Larsen C, and they are especially important outside of summer. So they occur year round, but particularly they account for a larger proportion of the melting that occurs in autumn and spring. And this is a really encouraging finding because it's bringing together previous work that's been done. For instance, this Peter Cooper's-Munike, his paper in 2018 that some of us contributed to, and then Andy Elvidge's paper in 2020. So initially I looked at the correlations, and we saw a positive relationship between the melt flux and sensible heat flux, and then a negative one between melt flux and latent heat flux, which is what we'd expect with Fern. And this correlation was largest in summer and autumn. But it doesn't tell us conclusively that it's to do with Fern, because it could indicate as well periods of warm air advection. So we need something of a better way to distinguish between Fern events and other kinds of events that would result in these relationships. So if we look at one example of one season, this is autumn, March, April, May. Again, we've got this surface meteorological composite on this side here, and the melting composite on the other side. We can see with really strong cross-peninsular flow that results in these like very strong winds, even at the surface, that are coming from the northwest, raising the maximum air temperatures sufficiently in some cases to result in melt. And you can see that it actually produces this almost exactly perfect east-west kind of curled around gradient that we saw in the satellite observations from of surface melting. So this suggests very strongly that this period of cross-peninsular flow is resulting in the melt anomalies that we see, and that Fern are associated with this. Now, the next step I went on, it was to diagnose the amount of Fern that occurs across the ice shelf. So that's the sort of the missing step that was often seen in the kind of relating Fern to surface melting. So what you've got in this plot is a spatial map of the mean amount of time as a percentage that Fern are occurring during the hindcast, so during this 1998 to 2017 period. What I've done is I've determined whether Fern are occurring using a method kind of adapted from one that John King used in a paper in 2017, which looks at isotopes, so constant levels of potential temperature, and whether Fern are occurring using this specific method. If anyone's interested, I can talk to you later about it. But the most important thing to see from this plot, and also from this table, is that Fern occur most frequently in the immediately of mountains, in the steep terrain. So the darkest colors are in the immediate in the inlets, and we can also see this in the data. So the ice shelf refers to ice shelf stations out on the ice shelf, so AWS 14 and 15 that I've used to validate, which are around about there, and then inlet stations, which are here in Cabinet Inlet, and then another one up here in Scar Inlet. And what we can see from the data and this is that inlet stations, you get much more Fern occurring. In fact, they occur 27% more frequently in inlets than ice shelves. And then also that Fern occur most frequently in September, October, November, so springtime, which is again consistent with the literature, which is again very encouraging. So this is essentially the missing step between finding where other studies have said, okay, well, this is the surface melting patterns, it would be consistent with a Fern-induced mechanism. And now we can see, using a kind of qualitative approach, that the concentration of Fern occurrence in the same locations in the northwest of the ice shelf strongly suggests that Fern are an important driver, at least, of surface melting over Larsen C. So this is almost filling in one of the missing steps. So inlet number 3, one of my favorite subjects, cloud. So on the right-hand side here, we've got a table of melt flux, of the correlation coefficients rather, between melt flux and a few selected variables. So downwelling, long wave and short wave, cloud fraction, and then ice and liquid water parts, which is a measure of the amount of ice and liquid in clouds. We know from previous slides that cloud exerts quite a strong control on the amount of shortwave radiation that reaches the surface, but it also impacts the amount of long wave. And I should caution that some of these correlations are quite low. So we do take them with a pinch of salt, but the data have an indication of the things that are important. And I think overall, the most important things that we can take away from this are that in summertime, a larger cloud fraction, so more cloud, and particularly when you've got more ice and liquid, those conditions, so cloudy conditions, are negatively related to melt flux. So that suggests that those conditions suppress melting. What's also interesting to note is that the cloud phase is important, so how much ice and how much liquid is in the cloud, and particularly liquid is an important control on melting. So when we have lots of liquid in clouds, that can impact the amount of radiation at the surface. The thing about clouds is that they have different effects in different seasons. So in summertime, when we have cloudy conditions, that prevents solar radiation reaching the surface. And you've seen the bottom two panels of this plot already. So this is the clear conditions during summer. And this is the kind of complementary figure. So we've got the cloudy conditions also in summer. Again, same kind of surface meteorological and then melt composites. In cloudy conditions in summer, we get negative temperature anomalies because less solar radiation is able to reach the surface, doesn't warm the surface quite so much, and that means we get lower balance of fluxes. So E total is smaller, and we also have a lower temperature, so we have negative melt conditions. You get much more solar radiation reaching the surface, and that raises temperatures and can cause melt in some cases. On the flip side, when we're considering other seasons, I've used the example of winter because it's the most extreme example. That's essentially the opposite case. So cloudy conditions actually warm the surface, so result in these positive maximum air temperature anomalies, and clear conditions lead to extreme cooling of the surface because we get lots and lots of upwelling long-wave radiation, and this is typical of wintertime stable conditions. So we get very negative Tmax anomalies. Usually the temperature is too low to allow for any melting, so that's why I've got 0 anomalies here, because you very rarely get any melting. So the effect of cloud is unimportant almost. In spring and autumn, the cloud actually increases the long wave flux, and if it's warm enough, can trigger melting. So, little brief summary. When we have very cloudy, often high liquid water path conditions in summer, that suppresses the amount of melting, because even though we have a slightly positive balance of fluxes, the surface temperature is often below the melting point because of the amount of solar radiation that's being reflected back to space. By contrast, in all the other seasons, the same cloudy, liquidy conditions can actually enhance melting because the amount of long wave radiation that clouds emit can increase the surface temperature. And if it's warm enough and the balance of fluxes is large enough, perhaps because there's enough liquid, this can actually initiate melting. So this could be really important actually in future. In Greenland, this is quite an important effect. So particularly low-level liquid-bearing clouds have been implicated in extensive melt events, such as we saw in 2012, I think 5 whole days where a very, very large proportion of Greenland was undergoing surface melt conditions, which is quite uncommon. So in future, this might be more likely to happen over Larsen C. So we know that clouds on Larsen C are associated with larger downwelling long wave fluxes, and that can be a slightly positive total surface energy balance. If temperatures are warm enough, then that can of course trigger melting. At the moment, the average temperature in March, April, May on Larsen C hovers around -1 degrees. So if projected temperature trends continue, as the pace of current climate change would suggest it might, then we might be more likely to see more cloud-mediated melting in the shoulder seasons of April and spring, or autumn and spring in future, and kind of a trend towards more Greenlandification, if you like. Finally, number 4 is the impact of large-scale circulation. So here you've got the angry plot of death, which is all of the composites from the high melt regime that I briefly mentioned at the beginning. So here, this regime is taking periods where melting is above the 75th percentile for each day. So this is when you get really intense periods of melting. And I'm looking here for the sorts of typical conditions that would result in those high intensive melt periods. So we've got composites for each season. And the thing that really stands out to me from these plots is that, first of all, in some seasons that aren't just when melting is everywhere, that some seasons you get this very clearly defined east-west gradient. And also that in all of these seasons, intensive melting tends to be associated with periods of cross-peninsular flow and northwesterly flow especially, which looks quite a lot to me like the pattern that is associated with, for example, a positive southern annular mode. So the southern annular mode is the dominant cause of variability in the southern hemisphere, and it is associated with strong westerly winds, particularly over the Antarctic Peninsula, and is also associated with the development of Fern winds. So here, this example is for autumn. We can see that during periods of positive SAM, you get, as expected, northwesterly flow. You get especially strong winds in the northwest of the peninsula and generally warmer Tmax anomalies. And characteristic, again, we get this east-west kind of gradient in the melting that is also observed alongside that. So we can assume or infer that the SAM and possibly the effect of Fern that it has this effect on melting, but we can do one step better, and we can try and look at the relationships between observed SAM and Fern frequency. So this table is showing you the correlation coefficients between the observed SAM index and the modeled Fern frequency for different seasons and then annually. And then we've got a visual representation of this in the plot on the left. So we've got every single season plus the annual relationship as well. So essentially it's showing that the large scale circulation patterns, such as the southern annular mode, are influencing the synoptic and local scale meteorology enough to drive these sorts of very highly localized effects like Fern winds. And it supports the idea that the trend towards a positive SAM, which is current and ongoing, may lead to greater Fern occurrence and hence melting in future. Now, a brief word about the regimes that suppress melting. So I've neglected those so far. So here we've got some composites showing regimes that reduce the amount of melting relative to the climatology. And this is taken for summer. Here we can see this is where we've got relatively low melt occurring. And here this is showing lots of southerly flow, if I find my pointer again. This is where we have melting below the 25th percentile, and you get lots and lots of southerly flow coming up from the Antarctic continent, indicating when you get katabatic outflow and suggestive of the development of a barrier wind, which is where you get this very strong wind along the side of the peninsula, generated by this flow of this cold, dense air off the continent and up along the edge of the ice shelf. And that's, of course, associated with negative melt anomalies. And this is a bit of a summary figure of all the large-scale circulation regimes, or generally the regimes that enhance and suppress melting relative to what we consider average. So regimes that enhance melting, as discussed, so flow over conditions, which are related to Fern events, positive SAM, which sets up those conditions for flow over and then Fern events, and then El Nino. So El Nino years are known to be related to positive SAM years. So basically all of these are showing the same thing. And then on the other side, we've got regimes that reduce the amount of melting compared to normal. So particularly barrier winds are very important. So this is where winds are very strongly flowing from south to north, and this results in very negative melt anomalies. Similarly, the negative mode of the SAM is associated with negative anomalies. And then the Larsen C low, which is actually quite interesting to me, because I think it's opposite to what I would expect. And I think that's probably related to the way I diagnosed it. So possibly some room for improvement there. Yes, as with this note, obviously these are all overlapping, so it's hard to discriminate between them. Okay, so the final chart rundown of the top 4 smash hits. In at number 1, we had shortwave radiation. Then the second most important driver of surface melting is Fern winds, and these are especially important in non-summer seasons. Then there's cloud. At the moment, not necessarily driving a lot of melt on its own, but could become more important in future. And then finally, large-scale circulation, which establishes the conditions for these more kind of localized and synoptic scale effects to have an influence. So this is just a summary in text form as well. So we know that shortwave radiation is important, fern drive melting in all seasons. We might see more Greenlandification, if you like, of Larsen C, and large-scale circulation establishes those conditions that either enhance or suppress melting. So that's me. Just a quick note is if you would like to use this data, I would absolutely love it. It's archived on CEDAR. It's a really big resource that I'm really happy for people to use. There's 3-dimensional outputs, 2-dimensional outputs. I'm very happy to have a chat or direct people in the right direction if you're interested in using any of it. There were so many things that I wanted to look at and didn't have the chance to do during my PhD. So if anyone has any need or desire to use the data, then please, by all means, do so. And then finally, I just wanted to use the opportunity when I've got so many Bath people as a captive audience to just say thank you. It's been an amazing 4 years I've had at Bath, and it's been really fantastic. So I'm very grateful to you all. So thank you all very much, and don't forget to stay in touch.